Okay, so now we are going to study some different topic known as converters, right? We also talked about some of the things, right? So we studied first order structure of filters, second order biquadratic and GMC implementation, right? So other than that, also we also studied switch cap filters also, where you have to replace resistance with switch cap circuit, which is like this, right? Where this phi 1 and phi 2 are non-overlapping one, and through that you can find out the equivalent resistance value, which is between V1 and V2. This is V1 and this is V2, right? So by tuning the value of clock and value of capacitor, sometimes you don't have access to change the value of clock, but you can change the value of capacitor. You need to make sure that capacitor value should not be very high, right? Something in picofarad is known as very big value. If you remember, like when you were in BTech, your teacher must have told you that if you are getting answer something in kilo ampere or ampere, right, in your analog course, then you are wrong, right? This is the thing my teacher also told me. If you are getting answer in kilo ampere or ampere, like it has to be in milliampere, right? All the like linear electronics, if you studied Milman Halkias or maybe Sidra Smith or whatever book you are following, we are not moving more than milliampere. It might be 100 milliampere, 200 milliampere, but the scaling factor has to be milli, right? So maybe you are in power electronics, then you can go to ampere, kilo ampere, right? But similar to that, if you are seeing something more than 1 picofarad, please stop yourself, right? 1 picofarad is a big number, at least for our case. It takes lots of area, so we don't use that generally. Similarly, there is no separate like uh, value for W, the biggest value. Somebody asked me, you asked me, right, that how much W is like possible. You can keep as big as, complete chip. Nobody is stopping you, but it takes area. Whether that area is possible for your application or not, that you need to see, right? For our case, I'll tell you some extra thing which is not told by you ever. Whenever you will go to any company, there are various views are there. Like when you are, this is by the way Cadence window, and I'm talking about views of Cadence. Different views of Cadence. One is called schematic view, layout view, right? Do you know any other? Hmm? Spectre. No, but Spectre is a caliber view, right? Where there will be parasitics will be there. Any other view do you know? GDS is a different thing. Look, it's not view. When you are opening it, view, you are not like. Don't you use view ever? There are lots of list is there. Like, very like view, yeah, right. So there are many views are there. How many views do you know? I'm asking you. So one of the view is abstract view. Let's assume that I'm a manager, and I'm you're running a company, and I'm going to I'm designing, let's assume that PLL, or let's make ADC, because ADC has following blocks like SAR ADC has. If you know, this is a comparator, there is a DAC, and there is this SAR. In SAR also, like there are some sub blocks are there, digital sub blocks are there, right? Digital sub blocks are there. So what I'm going to do, I have so many people, so I'll assign, let's say, comparator, one guy is going to make, let's say Siddhant is going to make, DAC, one more guy Saurav is going to make, Nishant is going to, let's say, he is manager of this particular block, and in under him I am keep giving him so many people, like 5 people are making these many blocks, right? So this is called I assign the work. But as I'm sitting on top, what I'm going to do, I'm going to make one diagram which I'm going to share with hierarchically who is sitting behind me, right? So let's assume that I'm going to tell him, look, this is the view I'm talking about. This abstract view is generally dealing with the layout. It's not at schematic level, but it is at the layout. And I know that SAR logic, if it is if it is comparator, how many pins do I need? Plus, minus, VDD, ground and out. So I'm going to write down here. I need ground. Let's assume that's ground here. I'll just similarly maybe I'll keep VDD over here. These are the pins, or they have to be, and orientation is already defined where which side I should have plus and minus. Maybe I'm going to ask here, and out maybe I'm going to ask here, because I am the one who is creating from top, and I'm going to ask comparator to be designed in this much area with exactly that position. I need to have VDD, out, ground and all these things. One guy is going to, let's say, make DAC, so I need DAC. So all these things will be decided by the manager, and he will tell you how much area and how much thing is actually needed, because his manager has already told him you have to design entire ADC for this area, and this ADC will go somewhere else and he will design something bigger thing, right? Maybe he is designing some complete mobile or maybe some processor, right, where this is going to be used as an abstract, and this is the thing which has been given to somebody. So he will take, let's say, 1 month. So everything has to be in parallel, right? Whenever one guy is completing the work, he will keep his abstract view here. So this is the thing which is known as abstract view, where all the blocks will be there with the pins at the higher level, right? This is called abstract view, right? So this is how your manager will tell you how much area is with you, and accordingly you have to design the view, right? So this is how generally all design engineers are making the budget of W, right? Maybe it will answer your, it is answering your question, right? Okay, now moving further, where I'm using chapter number 15 by John and Martin, and I'm talking about converter specifications. By the way, how many converters do you know? When somebody is telling you it's converter, what do you mean by converter? Hmm? No, it's not AC to DC converter, but yeah, okay, I'm keeping that also. Okay, okay, I should have add something called data converter. So if it is converters, so it may be AC to DC, but if it is data converter, it converts one form of data to another form. It might be analog to digital, digital to analog to digital, digital to analog, digital to digital is also there. Do you know about this? Not exactly that. Generally, when ADC, DAC, or this DDC, all are talking about digital output having, let's say, if it is 8 bit or 4 bits, 4 channels are there. Their code might be binary or any code. All are considered under one one uh, one umbrella, which is known as digital, right? The codes might be anything, but let's assume that 4 bits means 4 bits. 4 bits ADC or 4 bits DAC, 4 bit DDC. But what is DDC now? Sometimes some people having, let's assume that his image is very poor, or let's say very good image. in HD. I don't want in HD. I'm going to compress it, and I want poor one. I don't want something in, let's say, 20 megabytes or something. I want something in kilobytes. Then I'm going to use, this is also digital to digital, where I'm reducing the number of bits. Sometimes poor to, high quality. If I want to convert 4 bits to 10 bits, or 10 bits to 4 bits, this is called DDC. And something called TDC is also there. By the way, no problem in ADC DAC, right? ADC is analog to digital converter, DAC is digital to analog converter, DDC is digital to digital converter, and TDC is time to digital converter. So I want to convert time to digital. So generally um, in a system where you need to design, let's say, uh, how much time has been taken, you want to uh, show that in digital form, then you are going to use such kind of converter, which is time to digital. Let's assume that there is two signals are there. I want to capture one. So I want to capture this time, how much time it is. I can use simple XOR gate also, but I need to tell this time. Look, it might be the, femtosecond. Sometimes femtosecond cannot be captured, or picosecond, or millisecond. You need to capture small time. So how are you going to capture that time? That time has to be captured and has to be converted to digital domain. That is called TDC, right? So we are going to start with, actually, with the DAC, and there are some important terms. One is called discrete, continuous, and digital. So what is the difference between three? So discrete is quantized at time, right? Or the sample at time domain. So sampling actually is known as quantization, right? The word sampling is equal to quantization. So if you are quantizing x-axis, which is time, then it's discrete. If it is not quantized, available at each and every point, it's continuous. But if it is quantized even at amplitude level, means quantized both sides, then it's called digital, right? And you understand what is sampling. Whenever you are using sampling, you have to make sure that you're following the Nyquist rate. So what is Nyquist rate, by the way? Or the Nyquist theorem? Hmm? Right? Fs is generally dealing with the clock. The input frequency, I made it reverse. Input frequency has to be much lower than 2fs, right? Because 2fs will not work if it is like that. How do you make it something like this? So you are not going to see, you cannot reconstruct it, right? For reconstruction you need more points. So that's why we don't need just 2fs, it has to be much higher than 2fs, right? Okay. And there is something called quantization noise. Do you understand this? Like, these are the terms which is expected to be known, but if you don't know, then please let me know. Quantization noise, do you know? Okay, Nazrul, do you know? Yeah. So what is quantization noise? Or anybody who wants to try? Siddhant, do you want to try?
As the name suggests, at the time of quantization, it may possible we lose the exact amplitude of that
Okay.
some flat type of thing.
Okay, so you are right actually. So what Siddhant is saying, let's assume that I am sampling this here at different time, right? Similarly, I have to sample here also. So let's assume that I sampled and I got something like this. By the way, just remember that this points will not intersect in reality. When you are going to do the quantization here also, it's assumed that it's coming on top of this point. That's why this is happening. Otherwise, wherever the quantization is happening, it has to go there. What I mean to say, maybe your quantization levels are like this. Means I'll make, if this is your signal, there are two quantization I need to do at time level. So I'm doing, so this blue dots signifies the sampling in time, right? These are the discrete, but I am going to have quantization here. Both does not have any relevance, by the way. This is depending on number of samples and this is depending on your clock signal. This particular blue vertical lines are depending on the Nyquist rate. These black horizontal lines are depending on the number of levels or the resolution of your ADC, DAC or whatever. Don't worry about these words if you are not following. But are you following these two things, right? I am quantizing in both sides. Now I am trying to construct. So I'll start from here. At this time, let's say this is also available exactly at this point. Now I cannot go directly like jumping here or here, right? The next signal is available here. Like for time, this is available here, but I cannot go directly and I can draw this one. This is wrong because it has been quantized here. It can go only till this point. Again, second time I can go till here only. For third, yes, no problem. I can go here. For this one, I can not go here, but I can go here. For this one, I can go here, right? Okay, sorry, here and here, here and here. And let's assume that this is also there. So is it a good sampling or bad sampling? Okay, I made mistake. It has to be like this. This is the only thing. So now your square wave, sine wave looks like this one. Is it a sine wave or something else? So this is happening because of two reasons. What are those two reasons? One is, look, you have done two things, time sampling and amplitude sampling. So sampling clock is smaller. Number of levels are less. These are the two things. And because of what you are, instead of sine wave, you are saying something else. Whenever you are saying something else, that noise is known as quantization noise. Because this is happening because of quantization, as Siddhant has pointed out, right? So in both side, so what is the solution? One solution is follow the Nyquist, which is Fin has to be much lower than 2fs. Like just with 2fs will not work, because even if you are increasing so many levels, still your answer, like your reconstruction of the output will not look like sine wave, right? This is one thing. Second thing is increase number of levels as much as needed. But remember, you will never achieve sine wave. You will never achieve sine wave. Even if you have infinite number of levels, those levels will be 2 raised to infinity. But there will be some limitation. Maybe you experience that you are saying it's a 0 here. Very, very well written 0. In Adobe, maybe in Acrobat, you are saying. If you are zoom in, you are going to see it looks like this. These are the quantization noise which is playing the role, because it's digitally represented, right? Or some pixels are there, right? So now, any problem in understanding these terminology? Because we are going to use these terminologies. No, then we can move further. Yeah. Pratik, any problem? Okay. By the way, quantization noise we are going to denote with delta Q. Okay. In Nyquist rate converters, when I'm saying Nyquist rate converters, what do you think? What should be the meaning? In Nyquist rate converters, what is the meaning? What is it? And what is that? Fin has to be much lower than 2fs. Whenever I am saying fs is equal to clock of the system. There is a one-to-one correspondence between input and output values. There is one more thing. After Nyquist rate, there is something called oversampling. So when you are doing this Nyquist rate, okay, tell me one thing. If this is input, it might be anything. This is output. So this is linear or non-linear system. So are you going to see harmonics in your system or not? If there is no harmonics, so what will be the SNR of such system? Hmm? Why 1? Infinity. So SNR of any linear system will be infinity, because signal is at the fundamental has some tone. Other than fundamental, everything is 0, right? Because there is no harmonic. Second, third, because it's an ideal system, right? If the system is like this, what do you think about SNR? Is it linear or non-linear? Linear with some offset. Linear with some offset. Whenever you are saying offset, what does it mean? At DC frequency, you are going to see some value. Other than that, it's linear, right? If you are going to plot this one in FFT, you are going to see following frequency DC and fundamental. Here you have seen only fundamental. SNR of this system is also infinity, because SNR does not include DC frequency, right? This is DC offset. Okay. Now tell me, if it is like this, what are you going to see in terms of SNR? So this green color line, for sometimes it's 0, and after sometimes it becomes VDD. In square wave, you will have all the harmonics. So SNR will be very poor, right? We are not discussing how much right now, so but it will be very poor, the worst, you can say. if I'm doing this, what do you think? SNR between green line and red line, which one will have better SNR? Red one, right? Because it will have lower harmonics, right? So as you are increasing this, it will have better SNR, or it is trying to become straight line, right? When we are doing this, it's equivalent to increasing the number of levels. Look, when we are saying input and output, it's not playing the role of anywhere sampling. Look at this. There is no sampling. I'm not talking about sampling at all. I'm talking only in terms of amplitude of input with respect to amplitude of output, and that is getting sampled in y-axis. As you are increasing the number of level, SNR gets improved, right? So if you are having, let's say, 10 bits of ADC and one side 20 bits of ADC, 20 will have better resolution or better SNR. This is just one insight. Okay, one more thing. If you are using SNR, if you are using Nyquist rate converter, you are going to have certain SNR. But on top of it, if you are trying to oversample it, anything beyond 2fs is known as oversampling, by the way. Anything is beyond, like, anything is beyond 2fs is known as oversampling. How much oversampling you are taking? So Nyquist has suggested it has to be less less than or equal to. This is what he wrote, right? And thereafter it has been derived that it has to be much higher than this one. So the lower side is known as Nyquist rate. Even higher side is also Nyquist rate, but there is one more like another name which is coming under Nyquist rate, which is called oversampling. How much oversampling you are doing? 4 times, 8 times. So Fs by Fin, this ratio we are going to call oversampling ratio. If it is exactly equal to 2, we are going to call Nyquist rate, or 4, 8, all are Nyquist rate. But if it is oversampled by more than 2, it's called oversampling converter. If anything is more than 2, it's known as oversampling converters, not Nyquist. However, oversampling is also part of Nyquist. Both are synonyms at some cases, but at one point, when Fs by Fn is equal to 2, it's only Nyquist. It's not oversampled. It's just sampled, right? So, oversampling converter, when you are doing the oversampling, that will also increase the SNR by operating much faster than the input signal's Nyquist rate and filtering out quantization noise outside of the signal bandwidth. So what exactly this does when you are doing the oversampling, our main concern is where we are working in. Let's say this is the frequency where I am working. Let's call signal band frequency. I'm going to work on this. Let's say for some GSM band or whatever band you are working on, this is the frequency I'm going to work. And I don't care about other frequency, because before I'm looking at the output, I'm going to add one filter. So what I'm going to do, I'm going to reduce SNR very low in an in band frequency when you are doing oversampling, and outside this one you will see lots of harmonics, or maybe comparable to the input one. But we are interested only in this band because I am going to use filter after this. Such converters are known as oversampling converters, or this This is also sigma delta, which we are going to study, sigma delta ADC. How this is happening, that's a different thing. Till now we have not studied, but we are going to reduce the in-band noise, and all this in-band noise I'll dump it to out band. Right? So this is some technique through which people are doing the noise shaping, and that is what is written here. The Nyquist rate and filtering out quantization noise outside of the signal bandwidth, because that is what your main concern is. You don't care what is going to happen outside signal bandwidth, right? Okay, so data conversions have following things like data digital to analog conversion and analog to digital conversion, right? This is what we are going to study. It might be like, if you are looking from fast conversion or slow conversion or medium, depending on that, different architectures will be decided, right? But in broad way, if you want fast, you should use parallel architecture. If you want slow, okay, you can use serial, serial, right? So depending on what you want, really parallel is the best one, but it consumes more area. Here the trade-offs are area, power, conversion time. When I'm saying conversion time, that's the time when my data will be converted from digital to analog or analog to digital. But these are the terminology in general we are going to use: area, power, and conversion time. Right? So it's the trade-off between all these things, and thereafter other things are coming. Okay. So classifications of converters are as follows. You can have Nyquist rate converters or oversampling converters, where you are going to follow Fs by Fin as oversampling ratio. If it is more than 2, the converters are coming under oversampling converters category, where you are going to shape the converters by adding filter at the end. Because I am interested only in signal bandwidth. Let's start with the digital to analog converter. Any digital system is given to you, you have to convert it to analog. So if input is B1 times, so input is B in, when I'm writing B in with some dark arrow, there will be some number of bits. Let's assume that you have n bits are available. To convert it to V out in analog domain or decimal number, you can do following: B1 times 2 raised to minus 1 plus B2 times 2 raised to minus 2, and so on, Bn times 2 raised to minus n, right? This equation is already known to you. Yes or no? Okay. If it is known to you, I can do following to get the V out. V out is nothing but V reference time, that B in equation, that is going to convert to a value which I want in analog, because I can go from, so Vref might be equal to VDD. It's not compulsory, but it might be VDD. So that reference value needs to be known to us. Otherwise, like, because these are the numbers between 1 and 0, they have to be quantized to a VDD level, right? Okay. So what is the minimum value which I can detect from here? So here I understand, if all the values are 1, all the values are 1, and Vref is equal to 5 volt. What I'm going to see at the output, by the way? Huh? All these B1, B2, B3, B till Bn all are 1. Here it's Vref is equal to 5, so you want to say 5, right? Yes or no? Hmm? Double of 5, because it's both side. Yeah. So plus or minus 5, so it's 10 volt, right? Are you agreeing with me or not? What he has told, Vref is a quantity between VDD and ground, right? So there is something called ground which is not shown. So Vref might be some plus or minus value. So it's total value from VDD to ground. So that's how you are getting double. So here, if this is 1, if this is 1, can you do it for 4 bits and tell me what answer you are going to get? If this is 5 volt. How much you are getting? Okay, just wanted to. Hmm? No, 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 not in terms of LSB. You have to tell me in terms of numbers. Huh? 6875. Right? It's not 10 volt, by the way. What Nazrul was saying was wrong. You will never get 10. It's only Vira. Yeah. If I am taking 5 bits, can you now tell me what will be the answer? If all are 1. You can use your mobile or the way Himanshu is using, right? 375. So what this analysis is saying, I am having 0 to Vref which is available in amplitude. If there are, look at this, if there are n number of labels, these labels are n. So how many bits I can create from these n labels? Or let's go in different way. If one bit is there, I have two possibilities, 1 and 0, right? This is one bit, 1 and 0. If there are two bits, then I have four possibilities, right? Or you can say that if there are n bits, I have 2 raised to n number of possibilities. So if there are 2 raised to n number of possibilities or the labels, how many bits will be there? Yeah, so tell me. Hmm? Log n. Okay. Right. So, or other way around, if there are 2 raised to n number of levels, you have n bits, right? Let's make it easier, right? So if all the levels are 1, let's assume that there are, okay, let's start from here where we have started with 4 bits, or sorry, 4 levels, right? That was the first thing. 4 levels are there. These are not number of bits, but 4, sorry, 4 number of bits will give you this one, right? So in this case, you can reach only till here. When you are going to sample it, you can, earlier you have seen it, right? When we are doing this, you are like coinciding with sampling and the amplitude. You are going to decide where I'm supposed to keep my amplitude level. What I mean to say is this one. So if you remember, like, we were not keeping here, but we were keeping the level here, because wherever the coincidence was happening, we need to keep there, right? So in this case, you can reach till here, not beyond that, because this level is actually VDD, which is saturated one. You will never reach there. If there are only 4 levels, you will reach here or somewhere little bit higher than that, which is the quantization noise. And that is what we are seeing here, 4.6875. You wanted to have 5, but 5 minus 4.6875, that's the quantization noise you are seeing right now. Similarly, if you are extending this to number of level by 5 or the 5 bits, it becomes little bit better. If you are increasing number of levels even more, you are going to see better output, right? So this is what I wanted to tell you. So in that case, what is the minimum value of detection you can do? Minimum value. If reference voltage, when I'm saying minimum, means this small tiny step or the difference between these two steps, all are known as LSB, or least significant beat, or equal to resolution. So how much I can do that? So it's V reference divided by 2 raised to n, right? Because 2 raised to n number of labels are there. So V reference divided by 2 raised to n. This is going to tell me how much is the resolution, or the minimum value which I can detect. If it is lower than that, I cannot detect it, right? Let's assume that it's a 5 volt reference value, DAC is there with 10 bits. What is the minimum value I can detect, by the way? How much? So how much?
1004.
Yeah, so 5 millivolt approximately, right? Right. So 5 millivolt I can detect, but if I want to detect lesser than 5 millivolt, I cannot detect. Anything lower than 5 millivolt is as good as nothing. I can detect 5 millivolt, 10 millivolt, 15 millivolt, 20 millivolt. These are the levels. So if it is sine wave, and if these are the levels, these levels are decided by my ADC. So this is 5 milli, 10 milli, 15 milli, 20 milli, 25 milli, 30 milli, 35 milli, 40, 45, 50, 55, and maybe 60 milli. But if this particular, like this, I cannot detect anything, I'll detect only this line. right? And that is what you are seeing in your DSO. If it is less than some 10 millivolt, it's not able to detect it, right? Or it's seeing something junk value here and there moving, right? That's the noise coming from your devices of your DSO, and it's a stochastic. It's flicker noise or thermal noise. Those noises are there, and that is what you are detecting, right? So Vref by 2 raised to n is going to give you the 1 LSB value or the resolution, and 1 LSB is equal to 1 by 2 raised to n. This is the normalized number with respect to Vref. This is normalized with Vref. Sometimes some people are calling resolution is equal to number of bits also. Some people tell you that what is the resolution of your DAC, then you can tell that it's 5 bits. If you are going to say that 5 millivolt, he will not understand, because he needs to understand how much V reference you are going to use, right? So if somebody is not known to you, or he does not know your system, you should say that 5 bits, 6 bits or 10 bits, because in that case you don't need to define vref value, right? Okay, so data converters translates between digital binary codes and analog voltages or currents. In an ideal converter, the binary codes correspond to analog signal quantities that are precisely equally spaced. So I'm saying signal quantities that are precisely equally spaced means when you are going to do this sampling and quantization, this LSB will be equally spaced. But this is ideal situation. This is not going to happen in reality. You are going to see some different, spacing. This is just happening ideally. Look at this. This is only happening if it is ideal converter on paper. Otherwise, you are going to see different LSBs for different code. It has to be controlled. Okay. So now the illustration says that draw expected and ideal DAC characteristic if it is 3 bits of DAC. Can you draw that? So ideal characteristic, if it is DAC, what should be at x-axis, by the way? I want to draw DAC characteristic. What has to be at input side or x-axis side? It has to be digital, right? And output side, it has to be analog. In the case of ADC, analog will come to x-axis, y-axis will be like digital, right? What ideal characteristic we are expecting is this one. This is the ideal one. If you are designing 3 bits of DAC, means from here to here, input will have how many number of labels, by the way? Right, so 000, 010, 011, 100, 101, 110, right? Right. So as I told you, output is only possible at these intersections only. Other places it's not possible because it's a quantization noise. So from 000 to 001, if you are giving for a given LSB, output will be nothing. So let's assume that this is 5 volt, or let's assume that this is 1 volt, which is the maximum value available. Okay, one is here, one is your Vref. So what will be the value over here? No, corresponding to this value, analog value. Use your calculator and tell me. Is it correct, right? 1 by 2 raised to 8, how much? 0.125. What is this one? 0.25, 0.375, 0.5, 0.625. Now tell me. 0.75. What about this one? 0.875, right? So these are the different labels. They are equally spaced right now, ideally, right? They are equally spaced with the one LSB of 0.125 volts. By the way, analog is in volts, and this is digital code. So if your input is 001, then you should see 0.125 as output. If your input is 010, your output has to be 0.25, because nothing is happening in between. Look, nothing is happening in between, so other voltages will not be available, right? So I can draw. So you can see that you will never reach Vref of 1 volt. Even if you are applying all 1, your output is reaching just 0.875. If you want to increase it, you need to increase the number of levels. If you are increasing to 4, 5, 6, 7, 8, as you are increasing it, you are trying to reach V reference voltage of 1. But if you are increasing to 1, 10 number of bits, still you can reach something like this. Still there will be 1 millivolt of gap, approximately 1 millivolt of gap, right? So that will be the case, or that is the quantization noise which you are going to face in your circuits, whether it's analog to digital or digital to analog, right? Okay, so any problem in saying this, or any question? No question. Okay, by the way, what is this step size? Horizontal and vertical. Okay, so let's call this one as 1 LSB. This one also, let's call this one 1 LSB, because this is always square, exact square. From here to here, everywhere it's 1 LSB, right? One more thing, nobody has asked me. I made such approximation like this. This can happen that 001 is here, or 000 is here, and I'm starting from here. Around this characteristic, I can draw this. This is also possible, right? Still, ideal is at the middle only. It's not changing anywhere. Around that you can do that, or you can do this one also, right? I can do this one also. right? Like triple zero, at triple zero itself 0.125 is available. 001, there is something else, it keeps on going. In triple one, so I can do that also to reach exact 1 volt. You see, I'm reaching 1 volt, but still you can see that there is an offset at triple zero. So it's up to you how you are designing it, right? Or how the budget you are making. Sometimes you are going to see the characteristic which is not look like this one, but exactly like this. The ideal is look like this one, and around that you are making the budget. Such kind of thing is known as offset error. Or sometimes what you are going to observe, for all different labels. So you are expecting to make something like this or around this line, but instead of that you are around this line. Instead of getting output like this, this is also known as offset error. I'm referring this word offset error because this is happening because of the poor gain of your comparator. So you need to tune the gain such that it reaches this particular side, or it can reach VDD. This means that your gain is not sufficient to bring this to VDD, right? But even if somebody will get it, then we are going to declare that error as offset error, right? Okay, now the next question is, an 8-bit DAC has Vref is equal to 5 volt. What is the output voltage when B in is equal to 100 Tell me through your calculation. You have to add all those things, right? This is 8 bit, so so don't you have calculator which can convert this directly to decimal? Then you can multiply with Vref of 1, Vref of 5 volt. So these are the toy calculations, right? So what is VLSP? I believe you can do this, right? So what will be the VLSP? You don't have to tell me 5 divided by 2 raised to 8. You don't have to tell me 5 divided by 256. Huh? 0.0195. So what will be the unit of this one? Volts, right? So this is the most important thing. Without units, it's like nothing, right? Okay. Similarly, if you have the ideal ADC, just look at this. The input is V in, output is B out, and V reference is V reference. And you are going to have the output, which is V reference times B1 times 2 raised to minus 1 and so on, is equal to V in plus or minus Vx. This Vx is the one which is, although I'm calling this ideal one, ideal is this one with having infinite resolution. This is ideal ADC where analog will go to x-axis, digital will go to y-axis, because this is ADC whose input is analog, output is digital. By the way, what will be this value if this is 5 volt? V reference is 5 volt, so what will be this value? 0.0195, something like that, right? Just now you found out 195. No, it's for 8 bit, sorry. How much will be the value? 5 divided by 8. 0.625 volt. So anything which is less than 0.625 is as good as 0 for my ADC, right? And this VREF is deciding the maximum value. This is 1 LSB, right? What I was expecting here, by the way, before 0.625, let's assume that if it is 0.5 volt. At 0.5 volt, ideally what I was expecting, no, I was expecting, if it is infinite, I was expecting some value here. Maybe infinite, maybe something like this. Right? I was expecting some value, but it is not there. What I am getting? 0. Till what value I am going to see? 0. Let's call this one as Vx. So input is V in, which might be 0.625 volt. Until that, everything is junk for this particular ADC. But ADC is depending on the designer also. Maybe I'm the one who is designing, which is like this. Or maybe I'm designing like this. Right? Depending on that, the answer will change. So that's why I'm making one budget that let's keep something like plus or minus Vx. That plus or minus Vx is nothing but minus half LSB to plus half LSB range. So if this is 1 LSB, if I am starting from middle, let's assume that this is the ideal one, or this is the one which I am going to design. So there are two possibilities. One side is plus zero point 0.5 LSB and one is minus 0.5 LSB. If it is within this range, I am not going to see any error. This is what I am saying here, that V in plus or minus Vx will decide what side the code should go, because for different value you will have different answer, right? This is just for an insight. How it's going to happen, this is the future thing, right? But whenever you are this is, by the way, 2 bits of IO curve, and here this is analog and this is digital, which is ranging from 0 0 to 1 1, and it's equally spaced 1 1 by 4, 1 by 2, 3 by 4 and 1. But the characteristic has been started from middle. There is extra half LSB's offset is already there. That's why this is happening. If it is not there, then it would have started from here, right? So, but that much is allowed or not? Is it okay if we are giving half LSB offset? Is it okay or not?
Yes, sir.
Why?
Because it doesn't gonna affect the output
No,
and
it's affecting from 00 to 01.
it, giving a more clear output
Okay,
and
let's
picking up the power.
rephrase this question. Maybe you are right. If I am making 1.5 LSB of offset, is it allowed or not? So till 1.5, which is this one, and thereafter, is it allowed or not? I made a mistake here in drawing. Or maybe 2 LSB. Have I given? No, this is not 1.5. Yeah, 1.5. Is it okay or not? Why no? Your answer is correct. Okay.
Because it will never reach to the maximum level.
Excellent. So what you want to say is here still. Maximum level is not possible.
Yes, sir.
Like if I am getting half LSP, still there is no problem. I am getting all the levels from 00 to 11 because it's shifted. The whole thing is, if it is shifted within 1 LSB, there is no problem. You can see all the levels. But at the output side, as nothing is available here, can you see? It's nothing is available here actually. So this point will not happen actually, and you will not see this level in reality. So what we have to do, the quantization error, right now what we are seeing is quantization error in the IO curve. It has to be lesser than 1 LSB. If it is within 1 LSB, everything is fine. If you are exceeding 1 LSB, you will miss the codes at the higher side. This is the actually understanding you need to take. So it depends what kind of budget you are making, with floor, with ceiling, or with the median value. When I'm saying floor, means one guy is doing this, or one guy is doing this, or one guy is doing this one. Right? So green color is floor, blue color is ceiling, and black color is median value. So you have to make budget accordingly, and you have to make sure that your offset, or so there is only one Brahmastra we need to understand. Whenever any error in ADC or DAC, it has to be lesser than half LSB. I'm making this budget rather than making one LSB. One LSB could have been the better budget, but one LSB just keeping that as a budget is difficult. So let's keep zero point 0.5. Zero point 0.5 is extra margin for me. Even if I want to achieve zero point 0.5, I'll achieve something like 0 0.6, 0 0.65. Accordingly, all my equations will change. But I'm going to design it for zero point 0.5 so that at PVT, I'm going to achieve at least one LSB. Right? So this is what we need to do. I need to make a budget of quantization noise of half LSB extra, not one LSB, just to achieve that at different PVT. As long as it is not overloaded. The ideal quantizer introduces an additive quantization noise less than half of an LSB in magnitude. Somebody can explain this? This is same as what we talked, but somebody can explain. What do you think, Subham? This is the answer, what I asked you, and you gave it also. So So if I am taking 1.5 lsb of offset, what is going to happen? The output will be going beyond VDD before the all the codes are running. Maybe at for 3 bits at 7th code itself you are reaching VDD, right? So this is what it's saying. As long as it is not overloaded, means it's not reaching VDD or the overhead, right? The ideal quantizer introduces an additive quantization noise less than half of an LSB in magnitude. Otherwise, it will be higher. This is what it is explaining. And we are doing this just to make sure that all the codes should be visible. There should not be any missing code or like at the higher level, higher side. If you want to find out what the quantization noise associated with uh, your DAC or ADC, anything, then what you can do, let's say there is something called DFT, not vibes, DUT, design and test. So if it is ADC or DAC, let's assume that I want to find out quantization noise of DAC, then I am going to keep same number of bits of ADC just before this, and I am going to make such a setup where Vin is already known to me, right? Which is which may be ramp up signal. It has to be subtracted, or it may be like this also, whichever you like, and the output will be absolute value, which is going to give you some LSB. So here at the output, the difference between these two will be observed over here, and that will be declared as quantization noise, right? This is one way to determine the quantization noise. But if you want to find out ADC's quantization noise, same thing you can do, but you should have one DAC is available to you, right? Generally we are doing this in simulation. Get this, right? We are doing this in simulation, not in reality. In reality, what we can do, there is something called digital logic analyzer, which can be used to determine what is the quantization noise, right? Right now we don't have it one, but whenever we will have it, we will see that. Maybe very soon we should see that digital logic analyzer in our testing laboratory. So there you can determine how much quantization noise coming from your ADC. Like, so there is logic analyzer where different channels will be there, and it will tell you how much voltage is coming directly.
So in Cadence, we can analyze the FFT of that particular and get the
Yeah, that is also one possible thing. But through FFT, what are you going to do? Tell me. How are you going to get the?
we'll check for the how many different frequency
Mhm.
they are more than a minus 300 dB.
Okay, so okay, you are on right track, but I have not taught that. That's why I am not. Okay, okay. So tell me. So it is something like this. You are saying minus 300 dB is here. So what? So what? Okay, now this is fundamental. This is second, third, and fourth, and so on. Okay, so you are on right track. Okay,
We'll check for the magnitude and
okay, so magnitude. I check the magnitude. So what this magnitude is going to give me?
it will be lesser than fundamental.
Of course, listen, that it might be higher also. It's okay, fine. So it's a bad EDC. My agenda is to find number of beats of an ADC. I don't know what is number of beats right now. What we already talked about one technique through the quantization noise. By knowing the Vref value, if I am getting something like 0.125 and this is 1 volt, I know it's 8 bits, right? Second technique was logic analyzer. Third technique you are introducing. So tell me. It looks creative. That's why I'm asking you. So what? So through these magnitudes, what you can find out? You can find out SNR, which is called signal to noise ratio. And how to find out number of beats from signal to noise ratio, I'm going to tell maybe in next lecture. Okay, there is some equation through which you can find out. Maybe you studied in your BTech, I don't know. You studied it? SNR and number of beats, some equation. Okay. All the people who have studied instrumentation, they should have studied this. Saurabh, you studied instrumentation or electrical? Instrumentation? Somebody? Okay. All electrical are here. Sandeep, okay. Sandeep is not here. Because generally we like all instrumentation people, they study, DSO, logic analyzer as a course. Then they study everything in terms of SNR rather than talking in terms of resolution. They study in SNR. Yeah, of course, electrical don't study that. Communication can answer it. Nazrul, what do you think? You must have studied. Look, you are already PhD, right? You must have studied somewhere. This is a gate question also. No? In electronics, people like you studied Raman because Pratik is also electrical. So there is one equation through which you can find out because what Himanshu is actually designing is something like this. This is known as some sigma delta loop is there. So in this sigma, this is getting added on time and this is integration. So sigma and sorry, this is difference is delta and this is actually summation, right? Integration, sampled integration is summation, right? So this is sigma delta loop. So in this sigma delta loop, he is seeing only one output. There are not five five beats, 6 beats or lines are there. I need to find out from this one line how many number of beats I can create. That can be only seen by the SNR, right? So already Himanshu know the answer, but we'll discuss maybe next time, right? Because I need to give the derivation. If you want, I can just give you. This is the equation. I don't know whether you studied or not, but this is the equation.